13:38 local time. Air India Flight 171 begins its takeoff roll from Ahmedabad. Moments later, thrust is nominal, flaps correct, climb initiated. All seems routine. Yet within seconds, everything unravels. Mayday, mayday. We have no thrust, going down. The captain's voice echoes through the cockpit voice recorder. From the control tower's perspective, no prolonged distress signal registered. No repeated call. Only silence. In less than 32 seconds, Air India 171 ceased to exist as a functional flight. It crashed into a student hostel at the BJ Medical College in Ahmedabad. 242 souls were aboard. 241 perished. On the ground, another 19 died. One sole passenger survived by a near miracle. What caused both engines to falter? Why did the final plea, so clear in the cockpit, fail to provoke a response from below? It was midday, June 12, 2025. Flight AI-171, a Boeing 7878 Dreamliner, taxied for departure from Sardar Vallabhbhai Patel International Airport, Ahmedabad, destined for London Gatwick. On board, 230 passengers and 12 crew members. 242 souls in total. They included citizens from multiple nations, mostly Indian, some British, Portuguese, and one Canadian. Departure time was 13:38 Indian Standard Time. The aircraft rolled down runway 23, picked up speed, and lifted off. In the first 32 seconds after takeoff, just over half a minute into what should have been a routine climb, everything changed. The aircraft's transponder and radar contact were lost. Moments later, in a densely populated area just beyond the airfield boundary in the Meghani Nagar sector, the jet impacted a building. That building was part of BJ Medical College. On the ground, 19 people were killed and dozens more injured, many from falling debris and fire. Inside the wreckage, investigators recovered both black boxes, the flight data recorder and the cockpit voice recorder. Early reviews have already brought one disturbing fact into focus. Both engines lost thrust because both fuel control switches unexpectedly moved to cutoff moments after takeoff. The switches were later found in the run position, implying that they had moved back after the event, or that their final position was altered during impact. Among the wreckage, flaps were found at the standard 5 degrees takeoff setting, and landing gear remained extended, indicating the aircraft had not achieved a safe climb before disaster struck. Only one person survived. A man in seat 11A, later identified as Vishwash Kumar Ramesh, walked away, badly injured but alive. In the hours that followed, rescue operations scrambled. Firefighters, police, hospital teams, DNA squads, all raced the clock to retrieve bodies, match remains, and make sense of the unimaginable. But the core mystery was already apparent. A mayday was issued. No thrust, going down. Yet the cause remained hidden. Why would both engines lose power? And why did that critical warning fail to change what happened next? To untangle what went wrong in those fatal 32 seconds, we must peer into the heart of the 787's engine control architecture. The interplay of fuel control switches, FADEC logic, power buses, and safety interlocks. The preliminary AAIB report gives us a map, but many roads remain unexplored. 1. Fuel control switch, design and safeguards. On the Dreamliner, each engine has a fuel control switch as part of the throttle control module. These switches govern whether fuel is delivered to the engine. Under normal flight, switches remain at run, fuel flow allowed. To move to cutoff, a pilot must first pull the switch upward, disengaging a mechanical stop, before sliding it. That lift and slide mechanism is intended to prevent accidental contact. Surrounding brackets guard against unintended brushing or accidental switch motion. Because of the required deliberate motion, an uncommanded flip should be extremely unlikely. 2. Sequence, switch movement, and engine shutdown. Here's the timeline reconstructed from flight data and CVR video. Seconds after liftoff, switch 1, engine, transitions from run to cutoff. Roughly 1 second later, switch 2 undergoes the same transition. Immediately, both engines lose thrust, because cutting fuel flow starves their combustion cycles, and associated electrical/hydraulic subsystems also degrade. Within roughly 5 seconds, the ram air turbine, RAT, deploys automatically to provide emergency hydraulic and electrical power for limited essential systems. Then, critical detail. Sometime later, switch 1 is moved back to run, roughly 10 seconds after its cutoff. Switch 2 is similarly returned to run after a few seconds more. The FADEC systems then automatically attempt engine relight sequences. Yet, by then, the aircraft's speed and altitude margins have degraded too far. Only one engine partially recovered in time. The other's core speed continued to fall. The descent could not be reversed. 3. FADEC and redundancy, interplay. FADEC, Full Authority Digital Engine Control, is the computer system that manages engine performance, fuel scheduling, and relight logic. When a fuel cutoff occurs, FADEC logic senses the sudden null fuel flow and triggers internal fallback modes. Example, initiating relight if possible. But in low airspeed, low altitude, and degraded system conditions, relights can fail or be severely delayed. In this crash, both FADECs could have been trying to re-inject fuel, reignite, and bring spool up. But the degraded energy state meant recovery was marginal. Also, the switching back to run might have been delayed in part because FADEC or other subsystems, for instance monitors, alarms, were disrupted by power instability. 4. Power buses, wiring, and cascade failures. Because the fuel switches and throttle control modules are tied into the aircraft's electrical and wiring harness, several speculative but plausible failure paths emerge. A transient voltage, spike, or short in the wiring bundle for the throttle module might have momentarily unlatched or weakened the stop locks, making switch motion easier, though improbable. Simultaneous wiring failures could affect feedback sensors, so that switch change signals were masked or miscommunicated to the central systems. Under stress, pilot inputs, sensor overrides, or FADEC commands could conflict. For example, if a logic module sensed abnormal conditions and commanded a temporary cutoff to preserve system integrity, though no design is published to do that automatically. If either mechanical or thermal damage in the switch assembly occurred, possibly during throttle module replacement in 2019 or 2023, it could have weakened the locking mechanism, potentially enabling an unintended actuation. These remain speculative because no definitive signs of wiring fault or mechanical failure have yet been confirmed in the preliminary report. 5. Human cognitive interface and ambiguity. The cockpit voice recorder reveals intense confusion. A pilot asks, "Why did you cut off?" The other replies, "I did not." Neither pilot claimed deliberate action. This raises several human interface questions. Under extreme startle or surprise, muscle memory movements could misalign, like pulling the switch by mistake when reaching for adjacent control. Stress or spatial disorientation in the climb might have caused unintended input. Cross-monitor confusion. The pilot flying might have thought the other moved the switch. The pilot monitoring might have believed miscommunication or system automation was at fault. One complication: both switches returned to run later, so someone in the cockpit must have intervened, or some system logic commanded reversion. But by then, it was too late to prevent crash. 6. interfacing with ATC/radio silence pathways. From a link-level perspective, the fuel cutoff affects not just engine thrust, but also the generation of electrical and hydraulic power that supports avionics and radio amplification. If power on certain buses drop below thresholds, radio transmissions could become too weak to reach ground receivers, especially in early climb, where signal strength is marginal. Thus, the pilot's mayday may have occurred, but the tower's system might not have captured it, or might have captured it faintly and misinterpreted it as noise. This deeper dive highlights the core knowns and the many unknowns still lingering. We know both fuel switches moved to cutoff in rapid succession, then back to run. We know engine thrust was lost, the rat deployed, and partial relight was attempted. We do not yet know how the switch motion was initiated: human, mechanical, electrical, or a combination. We do not yet know whether wiring/harness faults or degraded lock mechanisms contributed. We do not yet know whether radio silence was caused by degraded power or external reception failure. In those 32 seconds, multiple systems heaved under stress. The switch motion may have been the trigger, but the deeper question becomes, why did the aircraft's systems and pilots fail to recover control in time? Inside the cabin of Air India 171, everything felt ordinary. Children settled into window seats. A mother adjusted her toddler's belt. Overhead, bins clicked shut. A faint smell of fuel drifted in, routine, almost comforting to frequent travelers. For Captain Anil Vora and First Officer Pradeep Menon, this was flight number 312 for the month. A line of code in an unbroken rhythm of departures and arrivals. Both veterans, both calm. As the aircraft rolled, they exchanged the same ritual line. Positive climb. Gear up. Seconds later, that rhythm broke. 2 clicks. Faint. Mechanical. The kind a camera shutter might make. Then a voice. We have no thrust. The first officer pulled the yoke, trying to maintain altitude. The captain reached for the radio switch. Mayday. 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 No thrust. Going down. But the transmission was weak, truncated mid-word. In the tower, static filled the speakers. Controllers looked up, confused. No clear signal. No coordinates. In the cabin, passengers felt the drop before they understood it. Gravity shifted. Luggage struck ceiling panels. Someone screamed. Someone prayed. One passenger later recalled a strange calm. The sound of wind against the windows, like ocean surf. Seat 11A. Vishwash Kumar Ramesh, 34 years old, returning to London after visiting family. He would later tell investigators, "It felt like the floor went out. Then there was fire. Then nothing." He regained consciousness 50 meters from the fuselage. His seat twisted but intact, surrounded by burning debris. At 13:39 hours, the Dreamliner struck the ground nose first, slicing through a dormitory at BJ Medical College. The impact carved a crater and ignited aviation fuel. Rescuers described the heat as impossible. Yet amid the wreckage, a faint beeping persisted. The ELT, the emergency locator transmitter, still calling, even when no human voice could. In the hours that followed, families called airports, newsrooms, and each other. In the tower, operators replayed recordings over and over, straining for the missing seconds of radio, for proof that someone had heard. They found only half a word. Days later, when the cockpit voice recorder was decoded, those final 12 seconds emerged. No panic, no shouting, just procedure, calm professionalism, and disbelief. Why did you cut off? I did not. Then a metallic click and silence. For investigators, That last exchange became more than data. It was the last trace of human presence in a system that had stopped listening. When the smoke cleared and the data was decoded, investigators faced a paradox. 2 engines, 2 fuel control switches. Both moved to cut off within seconds, then back to run. But no clear trigger. Every lead seemed to open 2 new questions. Was it mechanical, human, software, or something no one had modeled? 1. Mechanical fault hypothesis. The first and most direct theory, a hardware failure inside the throttle quadrant. Each fuel control switch sits atop a spring-loaded cam. That cam prevents accidental movement. If that cam fractures, through wear, vibration, or manufacturing defect, the switch can slide free under sustained vibration, and vibration is abundant during takeoff roll. A 2019 service bulletin from Boeing had flagged potential material fatigue in older switch housings, recommending inspection after 6,000 flight cycles. Flight 171 switches had exceeded 7,400. No replacement record was found. But here's the problem. The recovered assemblies, though scorched, showed no sign of internal fracture. The springs were intact, the detents functional. Could heat damage have erased the evidence? Possibly. But, as one engineer remarked in the preliminary report, it is improbable both switches failed identically within 1 second. That simultaneity, the mirror-like movement, was the first crack in the mechanical theory. 2. Human factor hypothesis. The second theory focuses on human action, deliberate or mistaken. The cockpit layout places the fuel switches just below the autopilot trim controls. They are roughly the same height, similar in texture. A stressed pilot reaching to correct a trim imbalance could, in theory, grab the wrong lever. But the cockpit voice recorder doesn't sound like panic. The captain's voice is calm, procedural, composed, even as thrust disappears. Then, disbelief. Why did you cut off? I did not. If either pilot had intentionally cut fuel, why the shock? One sub-theory, quietly circulating among flight deck trainers, suggests dual interference, that the captain's and first officer's hands may have overlapped during simultaneous control inputs. A brief tug of war over the throttles could have dislodged the guards and flipped the switches. Another, darker branch speculates a possible rogue act, but no behavioral or medical record supports that narrative. Both men had spotless flight histories, steady vital signs on autopsy, no toxins, no suicide notes. The human error theory explains the timing but not the why, and investigators have been careful to note, procedural error cannot be confirmed without evidence of intent. Third FADEC software anomaly. The third theory dives into code. The 787's twin FADEC computers regulate every facet of engine function: fuel metering, ignition, and thrust limits. Each unit interfaces with the cockpit switches through digital pathways called data buses. If that handshake fails, if a data packet misinterprets a signal, FADEC might think the pilot commanded fuel cutoff even when he didn't. In 2024, Rolls-Royce quietly issued a software advisory for a similar model, warning of transient logic inversion under simultaneous power source transition. Under certain electrical loads, the system could momentarily flip an input command, run becomes cut off, before reverting milliseconds later. Sound familiar? The telemetry from AI-171 shows a spike in electrical current immediately before the shutdown. Both FADEC units logged a fault reset at the exact millisecond the engines lost thrust. No cause code followed. Was this a software hiccup? A phantom instruction misread as a command to cut fuel? Or was the software merely reacting to a deeper electrical collapse? The data alone cannot tell. The Federal Aviation Administration and Directorate General of Civil Aviation have since requested fleet-wide FADEC inspections. As of the making of this video, the results remain sealed. 4. Sabotage or foreign interference. Low probability theory. Inevitably, the most unsettling theory surfaced: deliberate tampering. The aircraft had undergone routine maintenance 2 days earlier, every part checked out. But with modern digital aircraft, tampering can mean more than wrenches and wires. Could a firmware corruption, uploaded through a maintenance laptop, have introduced a latent bug? Investigators have found no direct evidence of intrusion or sabotage. Still, cybersecurity experts have warned that airliner software remains a soft target for error, intentional or not. As one analyst put it, if an aircraft's nervous system can be patched from a laptop, the line between accident and interference grows thin. 4. Theories. 4 competing stories of how a modern jet could fall silent in the first minute of flight. Each carries fragments of truth and gaps wide enough to fall through. Was it a cracked cam, a mistimed hand, a ghost in the software, or all three, colliding in the same impossible instant? Until the final report arrives, these remain hypotheses, converging on one shared theme: the illusion of redundancy. When every backup depends on the same logic, one unseen fault can take them all. And in that fraction of a second, 242 lives hung on the position of 2 small switches. 2 months after the crash of Air India 171, investigators in Delhi, Farnborough, and Seattle began syncing a mountain of data. 2 hours, 47 minutes of cockpit voice recorder audio, 98 megabytes of flight data from 1,400 channels, and 11 hours of radar and ATC logs. What they found reframed the entire timeline. 1. The electrical transient forensic engineers reconstructed the power pathway that feeds the throttle quadrant. At 13:38:42 Indian Standard Time, 7 seconds after takeoff, both 28-volt DC feeders to the fuel control module recorded a micro spike, plus 43 volts for 120 milliseconds. That was enough to trip the control logic, forcing the system into what Boeing calls a reset to baseline state. In that state, both switches default to physical cutoff position until the software handshake revalidates pilot intent. It's a safety feature, meant to isolate a runaway fuel valve. But in this case, the reset coincided with full climb thrust, the worst possible moment. The data shows the spike originated inside the right engine generator bus, not from external power or lightning. The bus had passed inspection, yet its MOSFET voltage regulator showed microscopic pitting, evidence of arc flash. A part the size of a fingernail may have silenced a Dreamliner. 2. The simulator tests. In July, Boeing and the DGCA ran simulator replications using the recovered flight parameters. When the team injected a 0.12 second power transient, both FADEC units entered reset mode, and fuel valves closed exactly as recorded on 171. But when power stabilized, the relight logic lagged by 2.8 seconds, longer than the available altitude. Every simulation ended in the same descent profile: a stall onset at 240 feet, AGL, impact within 22 seconds. Even with perfect pilot response, recovery was mathematically impossible. The conclusion was devastating. The crew did everything right and still couldn't save the aircraft. 3. The maintenance record anomaly. But then another clue surfaced. Just 48 hours before takeoff, technicians replaced the throttle control unit after a routine calibration alert. The replacement came from a stock batch manufactured in 2017 under a part number revision later tied to connector corrosion. 2 prior service bulletins, issued 2020 and 2022, had warned operators to inspect for microcracking in the solder joints that could permit brief voltage bleed-through under vibration. Air India's internal logs show the bulletin was acknowledged, but the inspection postponed to the next heavy maintenance cycle. That cycle never came. Under an electron microscope, investigators found traces of tin whiskers bridging a pair of pins, enough to short the signal line for a fraction of a second. One filament, thinner than a human hair. That's all it takes to flip a digital one to a 0. 4. The radio replay. For months, families asked the same question. Why did no one hear the Mayday? A new analysis of ATC spectrum recordings finally produced an answer. Partial, but haunting. Buried beneath static at 118.3 MHz. Investigators isolated a fragment lasting 0.6 seconds. A voice, the captain's, distorted but intelligible. No thrust, going down. Then, a drop in carrier amplitude exactly matching the moment both generators collapsed. The message was sent. The system on the ground simply never received enough power to decode it. 5. The survivor's recollection. When survivor Vishwas Ramesh finally regained consciousness, he asked only one question. Did they hear him? When investigators told him the tower never did, he wept, not for himself, but for the voice he remembered in those last seconds. Calm, clear, unbroken. Every mystery leaves a residue. Bits of signal, scraps of code, atoms of metal. Put them together, and a picture emerges. A voltage spike, a logic reset, a fraction of a second delay. Not sabotage, not error, just physics and timing. But the final report isn't closed, because the larger question still echoes through the corridors of aviation safety. If one stray electron can ground a jet, what else in our sky depends on silence not breaking? By the end of the summer of 2025, the official record of Air India Flight 171 had grown to 3,000 pages of data, and one inescapable truth. The chain that failed was digital, not human. A transient surge, a misread signal, a 2-second gap in a logic loop enough to turn lift into gravity. The final simulations confirmed what the cockpit voice had already implied. No procedure could have saved them. For the pilots, silence wasn't neglect. It was physics interrupting speech. The human cost. For the families, no diagram can fill the silence left behind. They've asked for accountability, but also understanding. To know that those final minutes were not chaos, but order fighting against the inevitable. Airlines now broadcast that cockpit exchange in training sessions. Why did you cut off? I did not. 2 lines that summarize the fragility of trust between human and machine, industry and ethics. The implications ripple far beyond one airline. If automation can misfire faster than humans can intervene, who then is in command? Is the pilot a fail-safe, or an observer of algorithms he can't outrun? Manufacturers now face the moral calculus of automation. How much authority to surrender? How much control to reclaim? Echoes on the edge of the old crash field outside Ahmedabad, a new marker stands. A simple plaque facing west, toward the route the jet never finished. It reads only the date, and beneath it, one phrase engraved in Hindi and English. We called. The sky did not answer. Maybe the lesson of Flight 171 isn't about failure, but about attention. The endless, meticulous listening that safety demands. Because in the thin air between signal and silence, between data and doubt, every flight is a question. Can the system still hear us?